In 28 through 42, use mathematical induction to verify the correctness of the formula you obtained in the reference exercise. Now we're doing exercise 12, which in exercise 12, we have the recurrence relation S sub k equals S sub k minus 1 plus 2k for each integer k greater than or equal to 1, and S sub 0 equals 3. The solution for number 12, which we didn't do in a previous video, is S sub n equals n squared plus n plus 3 for all n greater than or equal to 0. I'm going to stick with the variable n here because I want to ensure that our explicit formula is p of n instead of p of k to avoid that confusion from the last two videos. So this is what we're proving p of n. We'll start with the base case, which corresponds to when n equals 0. P of 0 is the statement that S sub 0 equals 0 squared plus 0 plus 3. But I'll put a question mark here because we don't want to assume the conclusion. We actually want to show this. We'll evaluate the left-hand side, S sub 0. Well, actually, this is given to us, so we could just say S sub 0 equals 3. And then we can evaluate the right-hand side, which is 0 squared plus 0 plus 3, which also equals 3. And so therefore, P of 0 is true because the left-hand side equals the right-hand side. Now let's move on to the inductive step. Let k be an arbitrary fixed integer with k greater than or equal to 0, and assume that P of k is true. So P of k is our inductive hypothesis, which is the statement that S sub k equals k squared plus k plus 3. We want to show that S sub k plus 1 equals k plus 1 all squared plus k plus 1 plus 3. Now, let's simplify that right-hand side so that we don't have to format the right-hand side in this very specific way. If we expand everything, this should be k squared plus 2k plus 1 plus k plus 1 plus 3. And if we group together our like terms, we get k squared plus 3k plus 5. So this is what we want to show. We want to show that S sub k plus 1 equals k squared plus 3k plus 5. The way we're going to show this is we're going to take the left-hand side here and do stuff to it. Now, since k is greater than or equal to 0, we can add 1 to both sides to show that k plus 1 is greater than or equal to 1, which means that we can apply the recursive definition here. This recursive definition only works for integers greater than or equal to 1, and k plus 1 satisfies that. So the recursive definition says that each term is the previous term plus 2 times whatever that value of the index variable is. So S sub k plus 1 is just going to be S sub k plus 2 times k plus 1. But we know what S sub k is. S sub k is k squared plus k plus 3 according to the inductive hypothesis. So we can do some substitution here and rewrite this as k squared plus k plus 3 and then plus 2 times k plus 1, which can be simplified to k squared plus 3k plus 5. And that's what we wanted to show, is that S sub k plus 1 equals k squared plus 3k plus 5. And that means that P of k plus 1 is true, which means that P of n is true for all integers n greater than or equal to 0 by mathematical induction. Thanks, everyone, and I'll see you in the next video.